Moving ahead from the combinational circuit designs, we would now explore another area of the digital circuits, and the major difference from the combinational circuits will be that we saw that in the combinational circuit the output depends on the present inputs only. However, we can actually develop certain circuits where the output will depend on the past output as well, or the past states of the system. So, that means that there is some memory activity. There is some memory in the system. That means it remembers what state it was, and depending on that, it would give the future state. Okay, what present state it is and what present input it receives, depending on that it will give its future state. So, it remembers the state of the system. So, this activity or this quality of the system is the memory of the system, and in this lecture we are going to start looking into how we can actually how we can develop the basic elements or basic units of memory, the basic units of memory, what that circuit is that we are trying to explore here. So, let us look at the available, these are, we know that these are the digital memory systems which are available in market, and what is the basic circuit there, that is what we are trying to explore. And this is the basic circuit. So, this is one of the basic circuit. So, let us explore this circuit, how this works, and that would give us a light on how we are actually implementing memory in a particular system. So, like here you can see what has happened in this circuit. We have connected two NOR gates in some sort of a feedback loop. So, you can understand that the output of one NOR gate is connected to the input of the other NOR gate. Okay, and this happens for both the NOR gates. Now, we have already designated the output sets as Q and Q bar, and you might tend to suppose that they will so there is no NOT gate connection between them, but why we are writing Q and Q bar? So, is it because that they are always giving complementary outputs, that is when one is 0 another would be 1, and one is 1 another would be 0, is it like that? So, the answer is not exactly so. So, we will explore why Q and Q bar is written here, but for the time being do not look at them as Q and Q bar, just look at them as two different outputs. One is the output of the, maybe you can call the R NOR gate, and another is the S NOR gate. Okay, the S NOR gate and the R NOR gate. So, we have these two NOR gates. Now, how to analyze a circuit? To analyze a circuit, what we need to do? We need to give inputs, all the various input combinations we need to give, and check what is the output coming from this circuit, and we have to construct a truth table according to that. So, let us do that simply. So, first the input that we are checking is S equals to 0, R equals to 1. We are checking this input first. So, now I have denoted the 0 and 1 with the red and green switches to make it more elaborate or pictorially represent it. But you can understand that the basic feature of the NOR gate is that whenever the input is 1, the output will be 0, it is bound to be 0. Okay, when one of the input is 0, we still do not know what would be the output, but when one of the input is 1, we are sure, we are guaranteed that the output would be 0. That means R being 1, the output of the R NOR gate will become 0. So, that is what happens. Now you see, when the output of the R NOR gate becomes 0, we can now do some prediction about the output of the S NOR gate. Before this, we are not able to do a prediction of the output of the S NOR gate. Okay. So now you can see this 0 output of the R NOR gate comes to the input of the S NOR gate, and that decides the output of the S NOR gate. What would be the output? We have both zeros in the NOR gate, so the output would be 1. So the output here would be 1. So you see 1 comes here. Now here previously it could have been something, but it did not affect the output, right? Because one input was already 1, so output would be 0. But now some input has come, so does it change the output? No, it will not change the input, because not change this output, because one of the input is already 1. So no matter what comes here, the output does not get affected. That means now this set of output is a stable output set for the combination S equals to 0, R equals to 1. So that is what is written here. S equals to 0, R equals to 1 would give you the output set like this. Now what we do, we check what would happen when we give S equals to 0, R equals to 0 from this condition. From this condition means that this output is 0 and this output is 1. When we give S equals to 0, so you see here S equals to 0, R equals to S equals to 0, R equals to 0, we have given. This was the output condition. Okay, so you notice from the previous that we have changed R from 1 to 0. Now we have to reanalyze what the circuit, how the circuit behaves. So now you see this was 1 which comes at the input of the R NOR gate. So again the R NOR gate experiences a 1 at the input. That means the output remains 0. It was previously 0, it remains 0. Also at the S NOR gate, both inputs are still 0 because this has not changed. Okay, both inputs are still 0 and the output remains 1. That means what happens basically, when you give S equals to 0, R equals to 0, given that your outputs are like this 0 and 1, that does not change the outputs. The output still remains 0 and 1. This is what my observation is. So when I give S equals to 0, R equals to 1, then I understood that no matter what the output was, it would change to 0 and 1. When S equals to 0 and R equals to 0 is given, starting from 0 and 1, it remains as 0 and 1. This is the conclusion now. Now we have to check for S equals to 0, S equals to 1 and R equals to 0, but before that there is a comment. The comment is this, that we are like since the output is not changing, we can say that we have achieved the memory state with S equals to 0, R equals to 0 for this particular combination. Starting from this S equals to 0, R equals to 1, so you have got Q equals to 0, Q bar equals to 1. Now if you give S equals to 0, R equals to 0, you will achieve the memory state. But does it happen the same way when we start from S equals to 1, R equals to 0? Let us see. So we have S equals to 1, R equals to 0. So when S equals to 1, that means this output of S NOR gate will become 0, definitely. So this becomes 0. So now the input of the R NOR gate both are 0, so output of the R NOR gate will be 1, and hence this would be the stable state. This would be the stable output. So this output will appear and then it will remain like this. And please remember, this output appears no matter what the previous output is, because of S being 1. S being 1 definitely changes your output of the S NOR gate. It becomes 0. Input of R NOR gate are both 0 now, so it definitely makes the output of the R NOR gate as 1. So whatever be the output before this particular input set was given, it changes and changes in this way, and it then becomes constant like this. So it is a steady output it is giving when we are having S equals to 1, R equals to 0, our output is 1 and 0. Now if we give the S equals to 0, R equals to 0, will the output change? So we are trying to, you can understand, we are trying to make the S equals to 0, R equals to 0 a memory state. So the condition should be that when we give S equals to 0, R equals to 0, starting from this particular output set, the output should not change. Then we can say that S equals to 0, R equals to 0 is memory state for this particular configuration also. Let us see, when we change S equals to 0, then you see this output was 1, so the input of S NOR gate still has 1 high. So 1 is coming at the input of the S NOR gate, and hence the output still remains 0. It does not change, and that means the output of the input of the R NOR gate are still having both zeros, so the output is still 1. So it is a steady configuration, and the steady configuration shows that the output has not changed. Hence we again achieve the memory state with S equals to 0, R equals to 0. What remains to be checked? We have not checked the configuration S equals to 1, R equals to 1. What happens then? Let us see. When S equals to 1, R equals to 1, obviously both of the outputs will be 0. Both of the outputs will be 0, and this is a steady output because these outputs will come back here at the input side, and this does not change anything because one of the input is 1. So the outputs will be 0, and this is a steady output. But what happens when we give S equals to 0, R equals to 0 starting from this output configuration? Then does it maintain this output condition? If it maintains, well and good, then we can say S equals to 0, R equals to 0 is the memory state for any configuration that you can give. So you can start from anywhere, and if you give S equals to 0, R equals to 0, it will not change the output. We can say that. But does it remain so? It does not remain so. What happens? Let us see. So now let us change S equals to S and R to 0. We have changed S and R to 0. Now what happens in the next step? You see these outputs will come at the input, and once it comes, both the NOR gates are experiencing 0 input, both 0 input. That means the output will become high for both the NOR gates, correct? So this output which was 0 0 does not remain that, it becomes 1 1 now. As it becomes 1 1, what happens? This 1 1 will try to go at the input of the NOR gates, and as it goes to the input, you can understand the output will again change to 0 0, right? The output again changes to 0 0, and again the output will come to the input, and again the output will change to 1 1. So this output changes, keeps on changing from 0 0, 1 to 1 1, 0 0 to 1 1. This output is unstable now. So the S equals to 0, R equals to 0 configuration which we were putting up as the memory step now becomes an unstable state if we are starting from S equals to 1, R equals to 1 input configuration. Okay, note that S equals to 1, R equals to 1 does not lead to instability. However, giving S equals to 0, R equals to 0 after the configuration S equals to 1, R equals to 1 will lead to this unstable configuration, unstable condition. Okay, now from the practical viewpoint, this system will not show up this instability. Why? Because so this is unstable, that is what we said. But now what I am saying is that from the practical viewpoint, this system will not show up the instability, because what would happen, you see that you must understand that there is some propagation delay of these NOR gates. That means when the input arrives at the NOR gate, the output is getting generated after some time instant, and this time, which is called the propagation delay or the gate delay. This gate delay will always be different for two different gates by some very minute fraction of second. It will be different, they cannot be same. That means one of the outputs will become 1 before the other output has become 1. So when you have given 0 0, so your previous condition was output was 0 0, so this is the stable condition, output 0 0. Now you have made R equals to 0, S equals to 0. One of the inputs will become high before the other input, one of the outputs will become high before the other output has become high. Correct. Let us suppose that this output of the R NOR gate has become high. Then what will happen? This will come here and this will not get a chance to become high anymore. It will remain low, and hence you can see again this output will not be changed. So this will become a stable configuration now. The stable configuration being output of R NOR gate is 1, output of S NOR gate is 0. But it might so happen that the output of the S NOR gate becomes high before the output of the R NOR gate becomes high. Then what will happen? Then this configuration will remain the stable configuration of the output, which is just the opposite of the previous stable configuration. Both are stable, but we don't know which one we will get. That is the problem. Both are stable. So when we are giving S equals to 0, R equals to 0, starting from the configuration S equals to 1, R equals to 1, which is giving output as 0 0. So now when we are giving S equals to 0, R equals to 0, ideally we would get instability that we showed, but practically we would get a stable output, but we don't know what that stable output would be. Will it be 0 1 or 1 0? We are not sure about. Whatever it can be, and whatever it becomes, it will remain like that. And one thing we note now, that even practically what we achieve is different from what we had got when we had given S equals to 1, R equals to 1. The output we had got that time was 0 0, and now when we have made S equals to 0, R equals to 1, the output is not 0 0 anymore. So with S equals to 0, R equals to 0, we are unable to achieve the memory state if we had started with the configuration S equals to 1, R equals to 1. And for this reason, what we actually do, we don't consider this input as a valid input. And if we can keep a check, so the user must keep a check that you are never giving S equals to 1, R equals to 1 to the input of this particular circuit. Then in the other cases, S equals to 0, R equals to 0 will be the memories. If you are somehow giving S equals to 1, R equals to 1 to this, if you are allowing to give S equals to 1, R equals to 1 to this circuit, then you cannot claim that S equals to 0, R equals to 0 will be the memory state. You cannot claim that. But if you are restricting yourself, or if you are restricting the user to give S equals to 1, R equals to 1, Then in the other conditions you see s equals to 0 or equals to 0 will be the memory state. So this is how we are actually defining the truth table. Then we are defining the truth table that s equals to 0 or equals to 0 will be the memory state. That means your q plus, which is the next instance q. So q is getting updated depending on the present q, right? So the updated q or the next q is q plus, and that is same as what q is right now. So this is the memory. When we are giving 0 1, we are getting output as 0 1. When we are giving 1 0, we are getting output as 0 1 0. When we are giving 1 1, the output will be 0 0, but this is not used. Okay, so we will not write this 0 0. We instead of we will write not used. Not used. Okay. So that is a situation. So we must remember that there is no practical instability in the SR latch. Okay, many places you might find this story of SR latch being unstable when we are giving combination 1 1. Why we are not using it? Because it is unstable. So this sort of answer is not accurate. It is stable, but we are unable to use it because the memory configuration will not work for this configuration. So the 0 0 we cannot claim it to be memory anymore if we are using 1 1. Okay, and ideally there is instability. Ideally there will be instability not with the configuration 1 1. The configuration 1 1 will give you a stable output 0 0. But the ideal instability will arrive when you give 0 0 input after 1 1. Then ideally there will be instability. So, but practically there will be stability, but it will not be the memory. So that's the situation. So that is why we avoid giving 1 1 at the input of the SR latch. This is the answer. So now another configuration is also there, which is with the NAND gate, and you notice the change in the position of the S and R as reversed in the NAND gate. And when we do that, the truth table will also get changed a bit. You analyze this circuit yourself by noting how I have analyzed the NOR gate circuit. You analyze the circuit yourself and you will find out that this is the particular truth table you will get. Here 1 1 would be the memory state. When you give input 0 1, your output will be 1 0. When you are giving input 1 0, your output will be 0 1. And now I hope you can understand why we are writing Q and Q bar at the outputs, because our design is such that we will always get complementary outputs from these two outputs. So these two outputs will always be complementary in nature, because we are not using the other input configuration which is giving me same output. We are always using those configurations which are giving me complementary outputs. So this is the story of a single latch circuit. But normally we are not using the latches like this. We are using the latches like what you are seeing in the circuit now. These are control latches. Here there is no additional input other than SNR. Now we have another additional input called the E input, which is the control input. We have studied the concept of enable input. So whether the circuit is operating or not, that is decided by the enable input. So that is the control on the circuit we are trying to get. So if we don't want this particular latch to operate even, we will make the enable input 0. So that is the only thing. But to give this enable input, we need another set of NAND gates or another pair of gates before this single latch element the single latch element that we just now studied, and we have to form the truth table of this particular controlled latch circuit. Now we already know the truth table of this particular portion, where the input now I have written as S star and R star. This truth table we already know. This is the NAND SR truth table. Now the NAND SR latch with enable, what we have to understand, that given particular combinations of S, E and R, what would be my S star and R star? That is what we need to understand only, because after that we will look into this truth table and can predict the outputs directly. Let us see. When we have 0 as the enable, then S star and R star will always be 1 1. Given 1 0 at the NAND gate input, output will become 1 1. So the 1 1 condition, S star and R star being 1 1, is the memory condition, you see. So no matter what S and R are, when you have 0 at the enable, you are getting memory condition. What does this mean? That means that we can say that the latch is not even working. So enable is 0, latch is not working, whatever its output are, it will stay like that. So it is as good as memory. Now when it is working, when we have activated the latch by giving E as 1, so when E is 1, then S star and R star are influenced by this S and R. So now if S and R are 0, then S star and R star will become 1 and 1, and then we are achieving the memory state while the circuit is in operation. Okay, this means the circuit is in operation, but still we are getting memory state. So the memory state configuration is achieved with S and R as 0 0. So the circuit still remains in operation, and we are only looking at now what is S and R and what would be S star and R star, because of this S and R that we are supplying. And you can notice that if S and R is 0 1, S star and R star would be 1 0, and the output would be 0 1. If S and R are 1 0, S star and R star would be 0 1, and the output would be 1 0. When S and R are 1 1, S star and R star would be 0 0, and this is the not used case. So by giving the control latch, another thing we have achieved. Previously the input output were a bit reversed. So when we are giving 0 1, output was 1 0 for the NAND latch, but now the NAND latch, the input and output are corresponding to each other. If we are giving 0 1, output is 0 1. If we are giving 1 0, output is 1 0. When we are giving 0 0, we have an intuition that when we are not supplying any input, the output will be memory. So it matches with our intuition, and 1 1 we are not using. So this truth table also becomes quite intuitive in nature when we are using controlled NAND latch. And this is the configuration we see most in practice, controlled NAND latch. Okay, and hence we would know the truth table of the controlled NAND latch also, and it is quite direct. S and R, whatever S and R is, output will be also that. Okay. One thing to note is that the output is influenced by S and R only. E is basically not influencing the output. So what should I say is that the output is updated depending on when we are giving the S and R pulses. Depending on the S and R pulses, the output is getting updated. The output is not getting updated depending on the enable input, which is the control input. We are treating the enable input as the control input, but the output is not getting updated with the change in the control input. It is still getting updated based on the S and R input. Hence, we can say that this operation is not synchronized with the control input, and hence we can call this as an asynchronous operation. So in the purview of sequential circuit design or sequential circuits, you will come across these terms synchronous and asynchronous. Synchronous will mean that the output will be changed based on the change of the input signal, control input, this enable signal. Okay, and when we are not able to change the output based on the change of the input control input, then it is asynchronous. That means the output can change no matter how the control input is changing. So the output can change depending on some other inputs which are asynchronous with the control input. So here S and R could change anytime, it does not depend on E, and the output is changing depending on S and R, it does not depend on E. Okay, so you might suppose that this would be the case always, but it is not so. So we will look into circuits where the output will change depending on the change of the enable input, and that is where we would like to go actually. Okay, but for the time being you understand that this is an asynchronous mode of operation. Now let us look into the control input a bit. What type of control inputs we can give to the circuit? The enable is a general square wave. We can give random aperiodic square wave pulses. Okay, so of any these on and off times can be very irregular in nature, it doesn't matter, and the SR pulses will affect the output whenever they are changed during EN equals to 1. Of course EN must be 1, but during this when EN is 1, during this time whenever you are changing SNR, your output is changing. It does not depend on your change of enable anymore. Okay, what about the clock? The clock is also like this enable signal only, but we have made the cycle periodic. And the duty cycle of the clock is defined as on time by total time period, on time by on time plus off time. Here also actually SR pulses can affect the output whenever they are changed during clock is high. That is true. So directly by using a periodic signal, we are still unable to affect the output at the change of the control input. We are still not able to do that, but we will utilize this clock signal actually, and it will lead us into synchronous circuit designs. How we will do that? We will look into that in the next lecture. So with this I end, and thank you for your attention.